I'm going to present on Intel CPU and a bunch of other random Intel knowledge that I thought was really cool and fun. So who am I? I'm a person. I'm on e-board, I guess. I'm on 2 e-boards, I guess. Go Weesus. Insert some pilot joke. I'm a second year. I like computer engineering. And don't talk to me about video games. I've played Pokemon, but I've never played Minecraft, and I feel like a lot of people get upset about that. Yeah. See, there are people. Okay. These are pictures. Most of my pictures are me either 0.5 or screaming, and it's great. These are the topics I'm gonna cover. I'm gonna cover some of Intel's history because Intel has an actually pretty cool history and website you guys should check out. I didn't cover much of the pretty cool stuff, but you guys can do that. What is an Intel CPU? The components of the CPU, and then the i9 core has the i9 core has 2 different cores. I'm going to talk about why 2 different cores and why that's important. Oh, the text is black on the thing. Okay, I highlighted it. It's cool. Okay. The history. So, Robert Noyce and Gordon Moore were Silicon Valley leaders in the tech industry in mid 1950s, and they were known for their amazing work with integrated circuits. They dedicated their time to create a new company to pursue their own innovations because they felt like their companies were kind of stifling what they wanted to create, and they named it Intel. Intel is short for Integrated Electronics. Because it's integrated circuits in electronics. So that's really cool. The DRAM, or the DRAM, Dynamic Random Access Memory. This was established for the semiconductor industry, and it became the new standard for a memory. This replaced magnetic core memories. So they used to be really fun magnets. And then the 4004 or 4004 was the first electronically programmable processor or microprocessor. So think of a device that accepts binary data from an input device and then processes the data according to the instructions stored in memory. So a good way to think about this is this was created in 1970. So they had no way to access something and reprogram it. Sort of, they would just build it in the way that it needed to work. And if they needed to make something work differently, instead of being able to reprogram it, they would have to make a completely different part. So this was one of the first devices where you could reprogram it for it to kind of execute a similar but different type of program so it could fit your needs, which I thought was cool. The i750, this is a programmable video processor that integrates full screen motion and digital video, audio, high-speed graphics. It was kind of the I is supposed to be lowercase, but it's fine. It was one of the products that I was I want to learn more about it. And it literally just gives you just random stuff. And it's just this is a thing Intel made, and it flopped. It flopped real hard. Even though it was really cool, it was just not as impressive because they were trying to kind of go outside their field of just making microprocessors and stuff. And it didn't work. And that was in the 1980s. When Intel became very, very unpopular. And then the Intel Pentium. So fun fact about Intel is they were told they couldn't trademark their namings of their cores and their CPUs for a while because they would just name it 365 and 788. And they were copyright was this is not allowed. It's too generic. So this is the first Intel chip. It's the 5th generation x86 chip that was named based off a number, and they kind of just kept the standard going from there. So what is an Intel CPU? Well, a CPU is a control processing unit, contains circuitry required to interpret machine-level programming instructions, and peripheral device processing. So peripheral devices could be printers, car readers, disk drives, and all of their processes completed by the CPU. In newer technology, this isn't really the case. In more modern tech, they kind of have a more significant amount of processing than before to offload some of the tasks from the CPU, but the CPU still has to interpret instructions coming from those peripheral devices. If you look at the picture, this is the processor package. The package is dropped into the CPU socket on a motherboard and is secured using like a locking level arrangement. A CPU cooler attaches to the processor package. If you ever want to like detach one of these, I would be careful. There's a lot of like different sockets that you have to be careful about, and also the number of contacts. A lot of them are like it's not standardized for like the points of contact or like where they connect. So you can rip like parts off your motherboard very easily. Very, very easily. You also have to make sure that you get the right CPU for a motherboard, I found out. Not that I know this, but for example, if you have the AM4A520 motherboards, they do not support the Athlon 200GE CPUs, even though both the motherboard and the CPU are AM4 and like made by the same company. They're not supported. Yeah. So a lot of the times when like if you go to like part picker, like PC part picker, definitely sort by category of like what works with what. That's very important. In fact, with Intel, most of their stuff isn't really like backwards compatible, I would say, because it's mostly like Intel motherboards and CPUs are generational. So they make the generations kind of interact with each other, and then they don't really let like a generation 12 interact very well with like a generation 6. So I would look into that. This is the cool part. This is a diagram of a CPU. All the text is black and I have to highlight all of it. Okay. So, the RAM and the system clock are not like part of the CPU, obviously, but they're like very important. So I kept like, I didn't make this diagram. I pulled it from the internet, but I was like, oh, well, I guess they're important enough to stay. So I didn't crop them out. But let's start with the ALU, or the arithmetic and logical unit. So this is the part that's going to be like doing the actions. And it's going to be taking input from like the A register and the B register. So can like Adam give me like a number 1 through 10? 5. And then Garrett give me a number 1 through 10. 5. Okay. So for arithmetic, for the arithmetic part, say like A register has 5 and B register has 5. The arithmetic will be like, oh, you have to add 5 and 5. So obviously that'll be in binary, so it'll be like 1 0 1. No, yeah, that's right. 1 0 1 plus 1 0 1, and then it'll add it together, and then it'll send it to the accumulator. And the accumulator basically like takes the output and not only just like transfers that, but it updates the instruction pointer, which I'll explain a little bit more. But that's kind of like how it works. And then for a logical unit, it'll be like, are these the same thing? And you have 5 and 5, and it'll compare, and then it'll give like a 1 or a 0, like 1 for yes if it's like active high. So like 1 for yes or a 0 for no. So that's really cool. So the instruction register and the instruction pointer, the instruction pointer specifies the location in memory containing the next instruction to be executed by the CPU. When the CPU completes the execution of the current instruction, the next instruction is loaded into the instruction register, which is then in the register from the memory location pointed by the instruction pointer, and then it's given to the arithmetic and logic unit so that way it can like calculate what is happening. And so like it's given what to do. So if you have like a code and like say you're debugging, or in C like you find out what pointers are when you like do 201, it's very similar to like that understanding of it, where it's like this is where the like you have this pointer because it points to like this location in memory, and it's the same thing. So it'll tell you where it is in memory for the instruction pointer. It'll go to like the catch and it'll find where it is, and then it'll give it to the instruction to the instruction register so that it can feed it into the arithmetic and logical unit. The catch or catch. I don't know how to pronounce it. Cache. I like catch better. The cache. Huh? Cache. The cache. I don't know. Cache. This is a simple CPU, by the way. Simple. So a lot more modern CPUs have multiple layers of cache. And there's like 2 like L1 like level 1s of cache, and you'll see why in a second. But CPUs never directly access RAM, so like random access memory. Most modern CPUs have 1 or more layers of cache because of this. So cache memory is way faster than RAM memory, like so much faster. Like a 6-year-old like racing against Michael Phelps, and the 6-year-old doesn't know how to swim like faster. At least that's like I like to think of it that way. So it's like the RAM's ability to feed data to the CPU is so much slower that the CPU needs to be able to perform these high-speed calculations somehow. So they keep that information in the cache, so that way they can access it faster. If they do need to like access the RAM, there's like predictive like algorithms, so that way they can like notify when they need like RAM information or RAM data, and it can access it that way. The cache controller analyzes the requested data and tries to predict that additional data from the RAM, so it can load the additional data to the cache in case it doesn't have it already. But that's only like if the information is not inside the cache already. So this is, like I said, a simple. So it has 3 levels of cache. Levels 2 and 3 are basically just like a bunch of data in case it needs to access it. They're designed to predict what data and program instructions will be needed next, and move the data from RAM and move it closer to the CPU so it's ready when it's needed. The level 1 cache is closest to the CPU, and this is the instruction cache and the data cache. So the instruction cache and the data cache. And the instruction cache is like with the instruction pointer, it'll send information, and so like when the instruction pointer has like the point of information, it'll get it from the cache, and the data cache will be where the data is. So like I said, with the arithmetic and logic unit being updated, it grabs it from there. So that's cool. Memory management unit. That manages the flow of data between the main memory unit and the CPU. This provides protection required. This provides memory protection required in multitasking environments, and conversion between virtual memory and physical virtual memory addresses and physical addresses. The CPU clock and control unit. It has to be synchronized. These processes can't be just like happening without like reason, because then there'd just be like a lot of waiting and stopping. So everything is synchronized on a clock cycle. So the more clock cycles you can have, like the faster your CPU is going to be happening. And the control unit performs this function at the rate of the predetermined clock speed. If you like look into like YouTube videos or like online, there are people who like can like simulate CPUs. I'll talk more about this later. There are people who can like simulate CPUs on like Proxmox or something like that, and they'll like up the clock speed like a ridiculous amount on like a random like CPU, and then it just like ruins it because it can't actually go that fast because the processes aren't like reacting that fast. So it's just like it's a mess and it doesn't really work. And that's why like everything is super calculated to how many clock cycles it can actually go through. So and then RAM, you know what that is. That's cool. So the CPU instruction cycle is the instruction, which could be like static data or pointers to variable data, is fetched and placed into the instruction register. The instruction is decoded and any data placed into A and B data registers. The instruction is executed using the A and B registers data, and the result is stored and it all happens in the ALU. And then the result is sent to the accumulator, and the instruction pointer is updated by a value, and the value is increased by like the length of the result. So however long, say it's like 4 bits, the instruction pointer is then updated like 4 bits, because that's where the next instruction in memory is. And then the process starts again. Okay, components of a CPU. This slide's kind of short. You have transistors indicated of performance. The more transistors, the faster the process is and the better power efficiency. For example, the i9 core has 17 billion transistors, and the i7 only has 10.3 billion. And the i9 is really cool, which I'll talk about later. Clocks, like I said, this is the rate of the CPU's ability to execute instructions. This is measured in hertz and cycles per second. E-cores, I'll talk more about the E-cores and P-cores on the next slide, but the E-cores are used for like background tasks, and the P-cores are used for performance. The P cores are very similar to traditional CPU designs with high clock speeds and like hyper-threading abilities. Yeah, and the E cores and P cores are specific to the Intel i9 chip, like the 12th generation. It's like one of I think it's their first chip they came out with both cores. And it's very indicative or very similar to how ARM does it. So if any of you guys know about ARM, they have like a similar thing with both high performance and energy efficient cores. They have like a big and little architecture. The big architecture handles like big processes that have to take place, sort of like when you're gaming or anything like that. And the little one handles like background things that are happening. So they've been working in tandem for a while, and Intel has decided to implement the same idea with their E cores and P cores. Kind of like copying, but it's not because it's engineering, so I don't know. But this is the first time that Intel has really done something like this, and it's like post-ARM has done it. So a lot of people are like, hey, that's interesting. But like I said, P cores are more powerful cores. They consume the most energy. They're the main cores. I'm trying to remember the amount of P cores. I think it's like 6 to like 8 maybe in the Intel i9 chip. I don't remember exactly. But in like the standard. So their main cores, they do the heavy lifting. They're based on the Golden Core architecture, if any of you guys know what that is. And they're for, like I said, gaming or other demanding tasks that will be handled by the P core. So if you have a huge like software, like an editing software, yeah, Devin? So if you're using Linux will actually like sort it, but how it does it is, I'll talk about this in a second, is it'll sort it by how like efficient it'll be. So I can skip ahead a little bit, but the P cores, if you were to like scale it, P cores run at 100% speed. They're going like the fastest, but the P cores have two different parts. They have part 1 for threading and the second part. So like imagine like 2 threads. So if you have 6 P cores and 8 E cores, 6 P cores, there'll be like, say you have 6 processes. They'll all automatically be put on the P cores. So on the first thread. And then say you have 7, because of like how speed works with like the second part of the P cores, it'll actually head to an E core if it's a lesser process. So then you'll have 6 events happening on P cores and 1 happening on E cores. If you fill up all the P cores and if you fill up all the first threads of the P cores, and then you go and fill up all the rest of the E cores, because the E cores only have space for 1, let's say, the E cores are running at about 50% of the speed as the P cores. The P cores then have the second thread, so it'll go P cores part 1, then to E cores, and then to the second part of the P core thread. The reason why it doesn't automatically go to the second P core thread is because that only runs at about 30% of the speed of the original P core. So you can think of it as like 100% for P core part 1, 50% for E core, and then 30% for P core part 2. E cores are smaller and weaker. They're all about power efficiency and providing the best performance per watt. They're based on the Gracemont architecture, and they're low power and low clock speed. So they're a little bit slower. They're also like smaller, and they consume less power. So they're very much built for efficiency rather than being able to do the most things at a time. They complement each other very well. Intel reports that the P cores in the 12th generation chip outperform 11th generation chips by about 19%, and the E cores outperform Skylake CPUs by about 40% when you're just using E cores. And for using the same amount of power as well. So the Intel E cores are still very, very efficient and very good. It's just in retrospect to the P cores that they're a little bit slower. They don't have as much like power. So why not just like use the high performance cores? Why not just use like P cores? Like I said, P cores, it's like 100% of the speed and then 30%. P cores are also a lot larger than E cores. So I read this article that was like, you want to have like 1 P core for every 2 to 3 E cores because of like the amount of space it takes up. And the proof is in the also E cores are about 20. The proof is in the pudding. Wait, I watched this video and it was, like I said, on Proxmox. It was really cool. And it basically explains what I explained to Devin's question, was they actually like ran a CPU just on E cores and they ran it just on P cores. And obviously like just running it on either one isn't like very successful. But when you ran it together, it was about like 30% more effective than just running it on P cores or just running it on E cores. And then it also proved the point of the speeds, like I was talking about, how it's like 100% for the P core part 1, and then E core part, and then the E core was 50, and then like 30%. So like the proof of like using like the separate instead of like having all the threads, like only having P cores or only having E cores, using them in tandem really shows that they're like very efficient together, and they're more efficient when you're using both of them, because you can like say you're running like, I don't know what, like Chrome takes, not Chrome, say you're running like Chrome and you're also running like a gaming like setup or whatever, the P cores are going to take the brunt of like the gaming setup, and then like the Chrome can be run on like the E cores, and it's not, you're not going to see like a total difference. There was a video that just ran, like it was like some gaming, it was a game, a video game, this is why I included gaming in my thing, that I can't talk about it, but they ran like a gaming thing, and it was just all numbers. They were like, it's running at like this like 80p, and like this is better than like this CPU, and it's just running on E cores, and I was like, good for you, man, you figured it out. So the performance, so yeah, I kind of just like rambled on for a little bit, sorry. But overall, they have 2 different cores because overall like super effective and efficient. And CPUs are cool, and I hope you understand how they work now. I've rambled, and Devin had me talk about my notes before my notes. And that's all. Thank you. Oh, and this is my works cited. Go to the YouTube channels, because I think you guys would really like, if you're really interested in it and like seeing how it works, like especially like in how like video games are like impacted by it. Look at it, and then you can use like VMs and like certain like services to like actually emulate like the CPUs just running on E cores and P cores. And same with ARM, you can just try running it on like big architecture and little architecture. Yeah, Chase.
If I was an underclassman and wanted to learn more, is there any upcoming opportunities that one could sign up for?
So Chase, for the stream, asked if he was an underclassman and wanted to learn more. Are there any opportunities to learn more about this? I mean, probably not specifically about CPUs, but Devin and I have a mentorship group, a hardware mentorship group that's super fun and swag that you guys should sign up for. But also, there's only like 6 spots. Or maybe Chase is going to put more people on there. I don't know, but you guys should sign up for it. It'd be cool. We're going to solder and do a bunch of other fun stuff. Yeah.
All right.
Yay! Oh, yeah, Sylvie? How do I spell solder? SOLDER. Is that right? Yeah, let's go!